Hi, welcome back to the class. Today we'll be learning about multi-dimensional arrays. So first going to two-dimensional arrays. So far we have explored arrays with only one dimension. It is also possible for arrays to have two or more dimensions. The two-dimensional array is also called as a matrix. Here is a simple example that stores roll number and marks obtained by a student side by side in a matrix. There are two parts of the program. In the first part, through a for loop, we read in the values of roll number and marks. Whereas in the second part, through another for loop, we print out these values. Look at the scanf statement used in the first loop. In stud I0 and stud I1, the first subscript of the variable stud is row number, which changes for every student. The second subscript tells which of the two columns are we talking about, the 0th column which contains the roll number or the first column which contains the marks. Remember, the counting of rows and columns begin with 0. The complete array arrangement is shown below. Thus, 1, 2, 3, 4 is stored in stud 00, 56 is stored in stud 01, and so on. The above arrangement highlights the fact a two-dimensional array is nothing but a collection of number of one-dimensional arrays placed one below the other. In our sample program, the array elements have been stored row-wise and accessed row-wise. However, you can access the array elements column-wise as well. Traditionally, the array elements are being stored and accessed row-wise. Therefore, we would also stick to the same strategy. Initializing a two-dimensional array. How do we initialize a two-dimensional array? It's as simple as this. Or even this would work. Of course, with the corresponding loss in readability. It is important to remember that while initializing a two-dimensional array, it is necessary to mention the second column dimension, whereas the first dimension is optional. Thus, the declaration int array23 is equal to 12, 34, so and so, and int array blank 3 is equal to 12, 34, so and so are perfectly acceptable, whereas int array 2 blank is equal to 2, 12, 34, so on, and int array blank blank is equal to 12, 34, so on would never work itself. Next, going to memory map of a two-dimensional array. Let us reiterate the arrangement of array elements in a two-dimensional array of students which contain roll numbers in one column and the marks in the other. The array arrangement shown earlier is only conceptually true. This is because memory doesn't contain rows and columns. In memory, whether it is a one-dimensional or two-dimensional array, the array elements are stored in one continuous chain. The arrangement of array elements of a two-dimensional array can be shown this way. We can easily refer to the marks obtained by the third student using the subscript notation as shown here. So, can we not refer the same element using pointer notation the way we did in the one-dimensional arrays? The answer is yes. Only the procedure is slightly difficult to understand. So next, going to pointers in two-dimensional arrays. The C language embodies an unusual but powerful capability. It can treat parts of array as arrays. More specifically, each row of a two-dimensional array can be thought of as a one-dimensional array. This is a very important fact if we wish to access array elements of a two-dimensional array using pointers. Thus, the declaration S52 can be brought off as a setting up of an array of 5 elements, each of which is a one-dimensional array containing 2 integers. We refer to an element of a one-dimensional array using a single subscript. Similarly, if we can imagine S to be a one-dimensional array, then we can refer to its 0th element as S of 0, the next element as S of 1, and so on. More specifically, S of 0 gives the address of the 0th one-dimensional array, and S of 1 gives the address of the first one-dimensional array, and so on. This fact can be demonstrated by using the program shown here. And the output for this program would be, let's figure out how the program works. The compiler knows that S is an array containing 4 one-dimensional arrays, each containing 2 integers. Each one-dimensional array occupies 4 bytes. So basically it occupies 2 bytes for each integer. These one-dimensional arrays are placed linearly, that is, 0th 1D array followed by the first 1D array. Hence, each one-dimensional array starts 4 bytes further along the last one, as can be seen in the memory map. We know that the expression S of 0 and S of 1 would yield the addresses of the 0th and the first one-dimensional array respectively. From the memory map shown here, these addresses turn out to be 65508 and 65512. Now, we have been able to reach each dimensional array. What remains is to be able to refer to individual elements of an one-dimensional array. Suppose we want to refer to the element S of 2 of 1 using pointers. We know that S of 2 would give the address 65516. The address of the second one-dimensional array obviously will be 65516 plus 1 would give the address 65518, or you can say S of 2 plus 1 would give the address 65518, and the value at this address can be obtained by using the value at address operator saying asterisk S of 2 plus 1. But we have already studied while learning one-dimensional arrays that num of I is same as asterisk num plus I. Similarly, asterisk S of 2 plus 1 is same as asterisk of asterisk S of 2 plus 1. Thus, all these given expressions refer to the same element. Using these concepts, the following program prints out each element of a two-dimensional array using pointer notation. And the output of this program would be, next going to pointer to an array. If we can have a pointer to an integer, a pointer to a float, a pointer to a character, then can't we have a pointer to an array? We certainly can. The following program shows how to build and use it. And here is the output for this program. Here, P is a pointer to an array of two integers. Note that the parentheses in the declaration of P are necessary. Absence of them would make P an array of two integer pointers. Array of pointers is covered in the later section of this class. In the outer for loop, each time we store the address of a new one-dimensional array. Thus, first time through this loop, P would contain the address of the 0th 1D array. This address is then assigned to an integer pointer pint. Lastly, in the inner for loop, using the pointer pint, we have printed the individual elements of the 1D array to which P is pointing. But why should we use a pointer to an array to print elements of 2D array? Is there any situation where we can appreciate its usage better? The entity pointer to an array is immensely useful when we need to pass a 2D array to a function. So now going to array of pointers, the way they can be an array of ints or an array of floats, similarly they can be an array of pointers. Since a pointer variable always contains an address, an array of pointers would be nothing but a collection of addresses. The addresses present in the array of pointers can be addresses of isolated variables or addresses of any array of elements or any other addresses. All rules that apply to an ordinary array apply to an array of pointers as well. I guess we should just go with this program to understand it better. And this particular memory map shows the contents in the arrangements of the array of pointers in memory. As you can observe, ARR contains addresses of the isolated int variables I, J, K, and L. The for loop in the program picks up the addresses present in ARR and prints the values present in these addresses. An array of pointers can even contain the addresses of other arrays. This following program would justify this. And I would like to leave it for you to figure out the output of this program. Next, going to three-dimensional arrays, we aren't going to show a programming example that uses a three-dimensional array. This is because in practical, one rarely uses this array. However, an example of initializing a three-dimensional array will consolidate your understanding of this subscripts. A three-dimensional array can be thought of as an array of arrays of arrays. The outer array has three elements, each of which is a two-dimensional array of four one-dimensional arrays, each of which contains two integers. In other words, one-dimensional array of two elements is constructed first, then four such one-dimensional arrays are placed one below the other to give a two-dimensional array containing four rows. Then, three such two-dimensional arrays are placed one behind the other to yield a three-dimensional array containing three two-dimensional arrays. In the array declaration, note how the commas have been given. I guess this particular figure will possibly help you in visualizing the situation better. Again, remember that the arrangement shown in this picture is only conceptually true. In memory, the same array elements are stored linearly, as shown in this particular memory map. How would you refer to the array element 1 in the above array? The first subscript should be 2, Since the element is in the third two-dimensional array, the second subscript should be 3 since the element is in the fourth row of the two-dimensional array. And the third subscript should be 1 since the element is in second position in the one-dimensional array. We can therefore say that the element 1 can be referred as ARR231. It can be noted here that the counting of array elements, even for a 3D array, begins with 0. Can we not refer this element using pointer notation? Of course, yes. For example, these two expressions refer to the same element in the 3D array. Let's just summarize what we have learned so far. An array is similar to an ordinary variable except that it can store multiple elements of similar type. Compiler does not perform bounds checking on an array. The array visible acts as a pointer to the 0th element of the array. In a 1D array, 0th element is a single value, whereas in a 2D array, this element is a 1D array. On incrementing a pointer, it points to the next location of its type. Array elements are stored in contiguous memory locations, and so they can be accessed using pointers. Only limited arithmetic can be done on pointers. So with that, we've come to the end of this lecture. In the next lecture, we'll be learning about strings. Thank you.